Hi students, welcome to our channel Physics Concepts by Ali sir. In today's session, now let's discuss about kinetic theory of gases. So, the first of all, now let us see the postulates of kinetic theory of gases. According to this theory, if any one container if is supposed to take, in the container millions of gas particles are present. The gas particles are, the shape is spherical and elastic in nature. These gas molecules are randomly in the motion. The size of the gas particles is very negligible when we comparing with the total volume of the container. These gas molecules used to travel in a particular direction, that is all the time they used to travel in a straight line. Then these gas molecules will exert pressure on the wall of the container due to the collision between the gas particles and the wall of the container, but not the collision between the molecules. Means if any one gas is exerting pressure on any one container means, so that is because of the gas molecules are continuously bombarding or colliding the container of the molecule. So once after these gas molecules are striking to any one particle, they used to travel in a straight line. For example, now let us take any one particle A. So this particle is then traveling and just striking to any one particle B. Then afterwards they used to travel in a straight line. So here is a C particle, and again this is a traveling, again here is a D. So these particles are traveling like this. Then here is the distance between the particles is, now let us take a lambda 1. The distance before the collision of any particle, lambda 1. This is a lambda 2 and this is a lambda 3. Like that n particles are there. Then we can find out the mean free path. So the mean free path, then lambda is equal to lambda 1 plus lambda 2 plus and so on plus lambda n by n. This is, we can call it as the mean free path of the particles. That is average distance travelled is called as mean free path of the particles. And again one more word also, now let us take the distance in between these two, the time is there, the time is called as time of relaxation. Means the time between the collisions. For example, the particle just it is starting and it is coming and colliding B. Before colliding, how much time it has taken for that collision, that is we are calling as the time of relaxation. That generally represents with the letter of T. So that is also average time of relaxation can be considered as this one. This is we are calling as tau, and again so that like that, then we can get the average relaxation time. Then we can take this is the formula to find out average relaxation time. And apart from that one, for this the mean free path. So for a mean free path we have still some more definition formulas also. So lambda is equal to 1 by root 2 pi n d square. This one we can take the formula for the average mean free path. The here by n is equal to number of particles and d is equal to distance between the two particles. This one also we can take lambda is equal to kt by root 2 pi rho d square. Also we can take the same formula, we can take even for the mean free path. These two formulas are very important. Okay, that is about basic assumptions about the important postulates also we can take. That is about kinetic theory of gases, and which has given by the Maxwell and Boltzmann. So the next one we can let us discuss about gas laws. From this gas laws very oftenly numericals are coming. Now let us discuss those gas laws. So gas laws, what are the gas laws we can take? The first one is Boyle's law. So what Boyle's law states exactly, at a constant temperature, pressure, so the pressure or volume is inversely proportional to the pressure at a constant temperature. So if you take any one container, then if you are increasing the pressure, volume will be decreased. if you are increasing the volume pressure, the both are inversely proportional. This one mathematically we can consider as PV is equal to constant, and for solving the numericals we can take P1 V1 is equal to P2 V2, and the graph we can take this is V we can take, and P, this is the graph will be a parabola or a curve. That is about Boyle's law. Next one, now let us go with Charles' law. So Charles' law that tells about that at constant temperature, at constant pressure, volume is directly proportional to the absolute temperature. So if we take any one container, pressure is constant. When we are increasing the temperature, volume of the gas will be increased. So if the temperature is decreased, volume also decreased. So this one mathematically we can take it as V by T is equal to constant. Also we can take V1 by T1 is equal to V2 by T2. So the graph we can take the temperature and volume, and so the graph we can take like this. And so this is actually this value is the absolute temperature value minus 273.15 degrees Celsius, then we can take. And the next one is Avogadro's law. Avogadro's law. According to this Avogadro's law, then volume of the gas is directly proportional to the number of molecules. So that is here is V is the volume and N is number of molecules. So more number of molecules are there, more volume will be. So then we can consider this one as V by N is equal to constant. Also we can take V1 by N1 is equal to V2 by N2. And here Avogadro's hypothesis. Now let us take two different gases. If these two different gases, now let us take in the two different containers under the equal condition of temperature and pressure, each gas occupies same volume, that is same number of molecules. So if we suppose to take still more example, now let us take at the gases at a 22.4 liters volume. So let's take two containers, A container, B container. In these two container, now let's take 22.4 liters of volume of the gas. Then these will be at under similar condition of temperature and pressure. Let's make those two containers temperature, pressure is a constant. So each gas will consist of 1 mole volume, that is 6.022 into 10 power 23 atoms are present in each gas. Under similar conditions of temperature and pressure, 22.4 liters of gas occupies, that is 6.023 into 10 power 23 atoms it is consisting. That is Avogadro's hypothesis we can take. Next one is Dalton's law of partial pressure. So Dalton's law of partial pressure we can take. Dalton's law of partial pressure. So what exactly meaning of this Dalton's law of partial pressure? Now the formula we can take P1 plus P2 plus and so on plus Pn is equal to P. P net also we can take. Means now let us take any one container. In this container P1 pressure is there, and so the gas pressure is P2, and in this container gas is there, the gas pressure is P2. Now these two pressures, now let us take these two gases in a big container. So the total pressure exerted by this container, the gas which are present in this container, that will be equal to the pressure exerted by the both the gases. That we can take. That is Dalton's law of partial pressure, what we can take. So the next one is Graham's law of diffusion. So what Graham's law of diffusion? That is Graham's law of diffusion. Diffusion means intermixing of particles in the gases. So for example, in any one room is there, when we are in the corner, when we are just spraying, that smell in the fraction of seconds that will travels to the all sides. That is we are calling as diffusion. Intermixing of molecules in the gas is called as diffusion. So the diffusion, according to this Graham's law of diffusion, the rate of diffusion is directly proportional to the 1 by root d. Also we can say the rate of diffusion is inversely proportional to the square of its density. are inversely proportional to the square of its molecular weight. Means what? The diffusion, the rate is, if the density is more, diffusion is less. Diffusion, molecular weight is more, diffusion will be less. If molecular weight is very less, diffusion is faster. That we can express as rate of diffusion is inversely proportional to the square of the density, or rate of diffusion is inversely proportional to the square of molecular velocity. So molecular weight, not molecular velocity, molecular weight. This one also we can take R1 square root D1 is equal to R2 square root D2. So this one also we can take. This is about the basic gas laws. Now let's go the next one. And so here is the most popular one. Now we are going to get, that is a real gas. So now what is meant by a real gas? Real gas is in sense. So now let us take first of all ideal gas. From that ideal gas, now we will discuss even a real gas also. Ideal gas. Ideal gas is a hypothetical gas. Now let us derive one expression for a ideal gas. So now for this one, 1, 2, 3 laws let us take. From the Boyle's law, V is directly proportional to 1 by P, and according to the Charles law, V is directly proportional to T, and again Avogadro's law, V is directly proportional to N. So by combining these three, LHS side we can find only volume. So volume is 1 by P into T into N. So then how it will get? V is equal to, then NT by, so V is directly proportional to NT by P. So we know that to remove any proportionality, we will use any one constant. So here V is, let us use R is the constant, R into NT by P. Then here is R is call it as a universal gas constant. Universal gas constant. That value 8.314 joule per mole, joule per or joule Kelvin inverse, mole inverse. So this is ultimately what we can write. PV is equal to nRT. This is we are calling as ideal gas equation. What is exactly the ideal gas equation? Ideal gas equation tells that PV is equal to nRT. P is the pressure, V is volume, N is equal to number of moles, R is a universal gas constant, and capital T is a absolute temperature. Now let us discuss about more about the ideal gas equation now. So this ideal gas is then what is meant by the PV? What is meant by ideal gas? If any one gas is following the PV is equal to nRT, such gas is called it as ideal gas. So what is meant by real gas? If a gas is not obeying PV is equal to nRT, then we can say that is a real gas. And so now first of all, now let's discuss about more about ideal gas. So this is ideal gas. So how this ideal gas changes? Now let us see. So PV is equal to nRT. Now if let's take at 1 mole, then what will happen? PV is equal to RT. This is one expression. This is one expression. PV is equal to nRT. And afterwards PV by RT is equal to constant. This one also then we can take. And next one, now let us learn one important formula, that is R is equal to NAK. Very popular formula this is. R is equal to, already we have learnt R. What is meant by R? Universal gas constant 8.314. Then this is what is N? A Avogadro number. Avogadro number, that is 6.023 into 10 power 23. Next K. K is called Boltzmann constant. So the Boltzmann constant 1.38 into 10 power minus 23. So that is the Boltzmann constant. Now we will take. So here is this expression. R is equal to NAK. You have to keep in mind. It is very popular one. So now in this situation, in the PV is equal to RT. PV is equal to, instead of R, now let us take a NKT. This is another popular formula. PV is equal to NKT. So this PV is equal to NKT. Now let us take still some more. Now let us take PV is equal to RT, and again now let us send V that side. So P is equal to RT by V. This one now let us multiply with M, divide with M. Then that is becomes how it will becomes RT into RT by M into M by V. So this M I have written here, this V we have written. This is equal to RT by M as it is. RT by M. MV means mass per unit volume. What do we call that is density. So this is another popular formula. P is equal to rho RT by M. Very popular this is. P is equal to rho RT by M. Whereas rho stands for the density. And afterwards now again the relation between the P is equal to one more formula also we can take, that is the pressure and kinetic energy. This is one more very popular formula. P is equal to 2 by 3 K. And again now let us take the relation between pressure and VRMS, root mean square velocity. P is equal to, then we will do 1 by 3. P is equal to 1 by 3. So rho M by V R square. VRMS. V is 1 by 3, rho M by VRM square. We can consider as this is we are calling as the relation between pressure and the density. So VRMS. Okay, right. Now again if you want to get, we have to draw one graph for PV is equal to nRT. So if we suppose to take so one side, now let us take PV by RT. And here now let us take a pressure, this side will take a volume, and PV is equal to PV by RT is equal to 1. So let us take, this is the value. And now if we suppose to take, this is an ideal gas. So ideal gas, now let us take, if we are taking the gas molecules, if one gas molecule will travels like this, and now let us take one more gas molecule also will be like this, and if you suppose take this another gas molecule also like this. So then what is meant by this T1, T2, T3. So here is T1 is greater than, T2 is greater than. This graph shows that this is these all are real gases. So real gases. Then what these gases? These real gases behaves like a ideal gas. At what condition? They will behave like a ideal gas. Then at then two conditions, at high pressure, low temperature. At high temperature and low pressure, then what will happen? These ideal gases, real gases behaves like a ideal gases. That we can take about the different PV is equal to nRT. These all things we can take. And so the next one, now let's discuss about different types of velocities. What are the different? Majorly in this topic we will discuss about three different velocities. One is VRMS, V mean square velocity. So here is how that is V mean square velocity. So that is then we can consider. So mean square velocity in sense, generally what is the formula for a VRMS is equal to square root of V1 square plus V2 square plus and so on Vn by n. What is the definition of VRMS, root mean square velocity? It is the square root of sum of squares of the velocities. Arithmetic mean, square root of arithmetic mean of squares of velocities, then we used to call it as a VRMS. So VRMS generally we can take like this, and afterwards VRMS is equal to, then we will get 3 PV by M. This is the formula one we can take, otherwise 3 RT by M also we can take. This is V mean square velocity. The next one is V most probable velocity. So most probable velocity, that is equal to 2 PV by M we can take, and also we can take 2 RT by M, then we can take this one, we can take even 3 KT by M also we can take, and this is equal to 2 KT by M also we can take. This is mean probable, then most probable velocity. What is meant by most probable velocity? Now if we suppose take any one container, in that container some gases are there. Once when we are keeping off, going on and taking off the gases, then which gas is frequently coming, that is the most probable. It doesn't mean that gas is having high temperature, low temperature, moderate temperature, doesn't matter. The more velocity, low velocity, doesn't matter. When we are taking that time, which gas is frequently that is existing, that is we are calling as most probable velocity. The most probable velocity, that is equal to square root of 2 RT by M. The next one is then V average velocity, V average. So then what is meant by V average velocity? Then we can take this is a 2 PV, then we are getting 2 PV by pi into M. Then we can take this one also, we can take 8 RT by pi into M. And this one also we can take 8 KT by pi into M. Then this is, if we suppose to take these ratios, how will we get the ratios? V RMS is to V most probable velocity is to V average velocity, that is equal to root 3 is to root 2 is to 8 by pi, this one we can take. And for this one then we can take again Maxwell distribution law and see how these graphs, this can be expressed in the graphs. So if we suppose to take the Maxwell distribution law, then according to this one, then again the gas is there. In that gas molecules are traveling with different velocities. Once when they are traveling with the different velocities, each gas is having each velocity. Means one velocity, one gas is having, it doesn't mean that all the gases are having the same velocity. Different gases are having different velocities they used to travel. The velocity maximum will be in between 0 to infinity. But maximum velocity of each gas we can take 3 into 10 power 8 meters per second. Means here the gas molecules can travel into the maximum speed of light, that is 3 into 10 power 8 meters per second. Now these gas molecules distribution, so that is now how these gas molecules, now let us see. For example, Maxwell's distribution law, if we suppose to take, then according to the Maxwell distribution law, Maxwell distribution law, now if we suppose take, we will get Maxwell distribution graph, distribution law, or also we can take a graph. Maxwell's law, what it tells is that, then now let us take, if we suppose to take any one gas like this, then here is now if we suppose the graph is like this, then here is the maximum peak is there, that we can take V maximum, then most probable velocity. The next peak will be, that is V average, and the next one, last one, we can take V RMS. But when you comparing with these all, V RMS is greater than V average is greater than V most probable velocity. And again one more also, now let us take. When we are supplying a temperature, then again what will happen? Different gases, the ones when we are supplying temperature, the molecules are getting temperature in sense, they shifts towards right side towards the graph. Now what is the meaning of that? Now once, now let us take. And here is now this is the graph one we can take, and this is one more graph we can take, and one more graph. Now let us take this one, and this is then cool air. So for cool air we will get this graph, and this is room temperature gas, that is the room temperature, and this one we will get the high temperature. So then a high temperature, once when you are taking the gases will be, this is the graph what we can take for different temperatures, these all things. Okay, no? Then afterwards, now let's see, this is Maxwell's Maxwell-Boltzmann distribution or distribution law of graph, law or graph for this one. And so the next one, now let us go with the most important, that is a degree of freedom. So the first of all, what is meant by degree of freedom? So degree of freedom states that now if we suppose to take any one container, in that container the molecules are traveling. Degree of freedom, it's very important topic, that is a degree of freedom. Then we can take, now let us take one more, that is a degree of freedom. So then what is meant by this degree of freedom? So this is a degree of freedom. What is the meaning of degree of freedom? This degree of freedom is generally represents with the letter of F. Now if we suppose to take any one gas in the coordinate system, how many possible directions the gas particle can move? For example, now here is any one container is there. In the container, one gas molecule is there. This is the gas molecule. And in that coordinate system, how many directions this can travel? Either it is traveling in one axis, this is x-axis, and this is y-axis, and this is z-axis. So these are the how many maximum possible directions a gas molecule can travel in any one given coordinate system. That is we are calling as a degree of freedom. So with the degree of freedom, we can find out the position and rotation and revolution of the gas particle in the gas. And so then how still we can more discuss about this one. And this degree of freedoms are basically three types. So the first one is then that is a translational degree of freedom. So what is meant by this translational degree of freedom? If we suppose to take any one coordinate axis, in this coordinate axis a molecule can travel this direction x-axis and y-axis and in this z-axis. So here is a degree of freedom, and for translationary motion maximum can be 3. And next one is then we can take rotational degree of freedom. So rotational degree of freedom, what is the meaning of this rotational degree of freedom? And so here is now the particle not only traveling in terms of this one, we can consider half mvx square, because in this direction, plus half mvy square plus half mvz square. So here is the three particles are the three possible directions are there, and that is why we have taken a degree of freedom is 3. And rotational degree of freedom. So if any one particle is we are considering the rotation. Rotation means what is that? And it is consisting when any one particle is in the rotation, it have the angle of the inertia of momentum. So then how much it will have the degree of freedom? So if your particle is in the rotational degree of freedom, it will have first of all linear, so half mvx square, then it will have, so then in terms of rotational degree of freedom, then we can take half ix omega x square plus half iy omega y square plus half iz omega z square. So these are three possible degree of freedom in terms of the rotational. So rotational degree of freedom, how many can possible? That is equal to F is equal to 3. And the third one is vibrational degree of freedom. So vibrational degree of freedom in sense, so this is not actually in our topic, but rotational degree of freedom can be possible at a high temperature. Whenever the high temperature is there, that time then we can find out the rotational vibrational degree of freedom. So now these all vibrationals again the degree of freedom. Now let us take first one for monoatomic gases. For monoatomic gases, how much is the degree of freedom? So monoatomic gas in sense, what are those ideal gases? Helium, neon, argon, krypton, xenon, radon. In these all situations, here is a monoatomic gas can act by only, then it can travel, it can have only translational degree of freedom. And so monoatomic gases degree of freedom is 3. Then why not it is translation degree of freedom only it can have. It cannot have then rotational degree of freedom because it traveling is in terms of the moment of inertia is very less, that is at most negligible. That is why that is for this one rotational degree of freedom is nothing, so 0. In terms of diatomic gases, so diatomic gases, now if we supposed to take, so what are those diatomic gases? And those all are hydrogen and fluorine, chlorine, bromine, iodine and fluorine, 82. These all things we can call it as a degree of diatomic gases. And they will have then actually the diatomic gases can travel in a translatory, and so they will have 3 degree of freedom in terms of plus, and they can travel in a y axis and z axis also, that is inertial momentum also, inertia of momentum in y axis z axis also can possible. And so maximum that is 2 only, because in the x axis that is present in the x axis in sense, then it is not possible for moment of inertia in x axis. So the diatomic gases, then we degree of freedom is 5. And triatomic gases, then triatomic, and of course we can take a polyatomic also. In this one linear, non-linear is there, together we will take for this degree of freedom is 6. So this is about briefly about degree of freedom for these all molecules. Okay, no? And next one is then the next one, the equipartition, the law of equipartition. So here is what is meant by law of equipartition. Now let us discuss law of equipartition in sense. Now let us see if any one gas or container. Now let us take in that gas. Now if we suppose to take one container is there, that container is in a thermal equilibrium. To that container let us supply some energy. Once when we are supplying energy, for example, for your understanding, so only for discussion purpose, now in that container only so 10 molecules are there. So now we are supplying so 100 units of energy. Then what will happen is 10 molecules, each molecule will be given same amount of energy. That is what we are calling as law of equipartition of energy. So then whatever the energy is supplied, the supplied energy is equally distributed among all the molecules. So that is what we are calling as law of equipartition of energy. So what exactly the meaning of this law of equipartition of energy? So this is equal to half kT. Means what is the meaning of that? Before we have discussed that in any one container is there, whatever the gas molecules are there, the given energy is supplied equally. So for example, x energy is supplying, and for this one x, this one is x, this one is x, even this one also x. That x value, how much is that? That is a half kT. So the amount of energy supplied, that is equal to half kT. So then we can take U is equal to what we can consider half kT. So this U for n molecules, Un is equal to 1 by 2 n kT also we can take n kT. In terms of degree of freedom, that is equal to F by 2 n kT also we can take. As we know that, and PV is equal to this one we can also consider as so U is equal to 1 by 2 kT. So PV also we can take, that is also PV is equal to then again RT, then we all take. And so he is ultimately, this is in terms of this U in energy in terms of the for any one degree of freedom, that is F by 2 n kT we are taking. Now let us write for this one. Assume that if n is equal to 1, in such a case degree of freedom of energy is equal to F by 2 into kT. So here if that is ideal gases, ideal gas in sense monoatomic gases. For monoatomic gas energy, how much is that? For monoatomic gas the energy U is equal to, so that is 3 by 2 kT. Why that is 3 by 2 kT? Because monoatomic gas degree of freedom is 3. So then what about diatomic gases? For diatomic gases, the degree of freedom, the energy is then that is equal to 5 by 2 kT. As here F is equal to 3 and here is F is equal to 5. Then this is a polyatomic or a triatomic gases. Triatomic gas, the degree of freedom U is equal to 6 by 2 kT as F is equal to 6. In this way, just we can take degree of freedom, each monoatomic, triatomic, those all things will have the same degree of freedom. Now, let us take the same concept about the in terms of specific heat. So for specific heat, what is the formula we have for a specific heat? So specific heat, dq is equal to du plus dw. So dq is equal to ncv dt. So then now we are going to discuss about this degree of freedom in terms of specific heat. The energy in terms of degree of freedom. So that is dq is equal to ncv dt. Then again, then here is du plus dw. From this one, that is at constant temperature, and so dw is equal to 0. Then what you will get, and again then we will get that is equal to, so u is equal to half kT we are getting. So half kT then we are getting, and du is equal to, then again then once we are just dq is equal to, so then what will happen, dq is equal to dw becomes 0, so du is equal to, then dq is equal to du, then du is equal to ncv dt, that is equal to half, then again pv and ncv dt then we can take, and here also this one we can consider as a half k delta t. So both sides we can cancel du2 d2 and half kT, then we can consider as in terms of monoatomic gases, what we got for this one, uf is equal to f by 2 kT, and so ncv is equal to k, what we have got for u is equal to half kT. So ncv is equal to delta t, du is equal to, then we got half kT of u by f by 2 kT, and so here is then ncv is equal to, then what we can consider is ncv is equal to, then we can, one moment Nana. Okay, right, here is now if we suppose to take now du is equal to f by 2 rt, so ncv dt is equal to f by 2 rt. Both sides dt can be cancelled, then ncv is equal to f by 2 r, where if we suppose take n is equal to 1, that time cv is equal to f by 2 r. So this is a specific heat of the gases at constant volume. Cv is equal to f by 2 r. The next one, then Cp minus Cv is equal to gamma. Then if we suppose take r, that is, then when we are taking, let's take Cp. Cp is equal to r plus Cv. R plus Cv value, how much we got? F by 2 r. So Cp is equal to, r can be taken 1 plus f by 2. So Cp is equal to, then this is what the formula for the constant temperature, the specific heat at a constant pressure. Then again, then Maid's equation, we get that Poisson's ratio. Then Cp by Cv is equal to gamma. That implies Cp value, how much is that? Cp value r into 1 plus f by 2 by Cv value, how much is that? F by 2 r, that is equal to gamma, and r get cancelled. Ultimately then we will get, so that value will get 1 plus gamma is equal to 1 plus 2 by f. So that is about the specific heat at a constant pressure and volumes. These all things we can take. So apart from this one, then we can take this is about the total values of formulas. Those all things about this equation. I hope that this session is helpful for you. Please support me and wish you all the best.